In the quiet hours of December 3, 1984, the city of Bhopal, India, was plunged into an unprecedented nightmare. A silent, invisible killer began to seep from the Union Carbide pesticide plant, initiating what would become the world's worst industrial disaster. This catastrophe wasn't merely an accident, it was a devastating culmination of systemic failures, where cost-cutting, neglected maintenance, and critical engineering oversights conspired to transform a seemingly minor issue, the failure of a single valve, into an unimaginable tragedy. Our story begins with the subtle signs of impending disaster. The Union Carbide India Limited, or UCIL, plant in Bhopal was established to produce 7, a carbamate pesticide, crucial for India's agricultural sector. A key ingredient in this process was methyl isocyanate, or mic, a highly volatile and profoundly toxic chemical compound. The plant was designed with safety protocols typical of its era, yet the inherent dangers of mic mandated unwavering vigilance in its handling and storage. The choice to manufacture and store such a lethal substance demanded the highest standards of engineering integrity and operational discipline. Methyl isocyanate is a compound of extreme reactivity. Exposure, even in small doses, can cause severe respiratory distress, blindness, and death. For bulk storage, mic required refrigeration to remain stable and prevent exothermic reactions. It was stored in 3 large underground tanks at the Bhopal plant, E610, E611, and E619. Maintaining a temperature below 5 degrees Celsius was paramount, a critical design feature intended to keep the chemical inert and safe. This fundamental requirement underscored the necessity of robust, continuously operational safety systems. To mitigate the extreme risks associated with mic, the Bhopal plant incorporated several layers of safety systems. These included refrigeration units for stable storage, a vent gas scrubber designed to neutralize escaping gas, and a flare tower intended to burn off any gas the scrubber couldn't handle. Collectively, these systems formed a critical defense in depth, each acting as a safeguard against potential leaks or accidental releases. The theoretical framework was sound, but its effectiveness depended entirely on meticulous maintenance and operational integrity. By the early 1980s, the Bhopal plant faced declining profitability. This economic pressure led to severe cost-cutting measures, which tragically impacted critical safety protocols and maintenance schedules. Staff reductions meant fewer skilled workers, and vital components were left unmaintained or even decommissioned to save money. This systematic erosion of safety standards created a perilous environment, gradually dismantling the layers of defense that were once meant to protect both the plant and the surrounding community. It set the stage for disaster. One of the most critical safeguards, the refrigeration unit for the mic storage tanks, had been shut down 5 months before the disaster. The rationale was simple: saving energy costs. This decision meant that the mic in tank E610 was no longer kept at its stable, low temperature, making it vulnerable to exothermic reactions. The inherent instability of the chemical, left unchecked by a deactivated cooling system, was a ticking time bomb. This single economic choice bypassed a fundamental engineering principle designed to prevent catastrophe. Another critical defense, the vent gas scrubber, designed to neutralize any escaping mic gas, was also out of commission on the night of the leak. It was reportedly undergoing maintenance or simply not activated. Without this crucial system, any gas release would go directly into the atmosphere, unmitigated. This meant that the first line of active defense against a mic leak was effectively non-existent, leaving the plant and the population exposed. The cumulative effect of these bypassed systems was a catastrophic loss of redundancy. The final major active safety system, the flare tower, intended to incinerate any gas that escaped the scrubber, was also not operational. A pipe connecting the relief valve header to the flare tower had been disconnected for maintenance, and it remained so. Even if it had been connected, the flare tower was designed for smaller, controlled releases, not the massive volume of gas that was about to erupt. With the refrigeration, scrubber, and flare tower all incapacitated, the plant's layers of engineered protection had been systematically dismantled, leaving a direct pathway for disaster. The immediate catalyst for the disaster was the entry of water into mic storage tank E610. On the evening of December 2nd, workers were attempting to clear a clogged pipe near the mic tank using water. Critically, a faulty pressure gauge and a poorly maintained valve allowed this water to flow directly into the mic tank itself. This was the single, direct mechanical failure that initiated the catastrophic chemical chain reaction. This valve, overlooked and undermaintained, was the weakest link in an already compromised safety chain. The critical component was a single slip-blind valve, part of the process line being washed. Designed to prevent flow, its failure to adequately seal allowed several hundred liters of water to mix with the stored mic. This wasn't merely a small leak, it was a breach of containment directly into the heart of the most hazardous material. The valve's inadequacy, likely due to corrosion, lack of proper inspection, or incorrect installation, highlights a fundamental breakdown in maintenance and engineering quality control that directly precipitated the tragedy. Once water contacted the mic in tank E610, an aggressive exothermic reaction began. With the refrigeration system off, there was nothing to dissipate the heat generated. The temperature inside the tank rapidly escalated, causing the mic to boil and vaporize at an alarming rate. This uncontrolled chemical runaway reaction generated immense pressure, far exceeding the tank's design limits. The combination of water, heat, and highly reactive mic created an unstoppable force within the containment vessel. Inside tank E610, the pressure continued to mount to dangerous levels. The tank, designed to withstand a specific pressure threshold, was being subjected to forces it was never meant to contain, especially with its refrigeration off. The boiling mic, turning into gas, expanded rapidly, exerting immense stress on the tank's structure. Alarms were triggered, signaling a critical situation, but by then, the reaction had become self-sustaining and irreversible, turning the storage tank into a pressurized vessel on the verge of catastrophic failure. As the internal pressure reached critical levels, the tank's final mechanical safety device, a rupture disc, failed. Designed to burst and release pressure before the tank itself exploded, this system functioned as intended but led directly to the gas release. However, because the scrubber and flare tower were inactive, the vented gas had no containment or neutralization. The bursting of the rupture disc, a last-ditch effort to prevent an even larger explosion, unleashed the toxic cloud directly into the environment. Between 12:30 a.m. and 2 a.m., approximately 40 tons of methyl isocyanate gas billowed out of the plant, forming a dense, deadly cloud that hugged the ground and drifted directly over the densely populated residential areas surrounding the factory. Carried by a gentle breeze, the gas spread swiftly, reaching thousands of unsuspecting citizens in their sleep. This was the moment the engineering failures culminated in a horrifying, real-world consequence, a toxic plume engulfing an entire community. The immediate impact was devastating. Thousands awoke to burning eyes, respiratory distress, and violent coughing. Panic ensued as people stumbled through the dark, blinded, and choking. Hospitals were overwhelmed, doctors unsure how to treat the unknown gas. Estimates suggest between 3,000 and 8,000 people died in the immediate aftermath, with many more suffering agonizing deaths in the following days and weeks. This night became a grim testament to the catastrophic human cost of industrial negligence and engineering failure. The toll of the Bhopal disaster didn't end with the initial deaths. Hundreds of thousands were permanently injured, suffering from chronic respiratory problems, blindness, neurological disorders, and severe birth defects in subsequent generations. The soil and groundwater around the plant remained contaminated, perpetuating a cycle of illness. The long-term health and environmental consequences underscore the enduring, devastating impact of a single industrial catastrophe, a stark reminder that the cost of negligence extends far beyond the immediate moment. Subsequent investigations meticulously pieced together the sequence of events, confirming the central role of mechanical failures and operational negligence. The faulty valve, the deactivated refrigeration, the non-operational scrubber and flare tower each represented a failure point in the plant's safety systems. These weren't isolated incidents but symptoms of a broader managerial and engineering culture that prioritized cost-cutting over safety, allowing critical infrastructure to deteriorate without consequence. The analysis highlighted how seemingly minor lapses accumulate into monumental risks. The Bhopal catastrophe served as a brutal awakening for industries worldwide. It highlighted the catastrophic potential of hazardous processes and the critical need for robust safety management. Nations and international bodies reacted by implementing far stricter regulations, particularly concerning chemical plants and process safety. The disaster forced a fundamental re-evaluation of how industrial facilities handle dangerous chemicals, shifting focus from reactive measures to proactive prevention through design and operational integrity. It became a global benchmark for industrial responsibility. A direct outcome of Bhopal was the formalization and widespread adoption of Process Safety Management, or PSM. PSM is a systematic approach to managing highly hazardous chemicals that focuses on preventing releases by addressing the processes, technologies, and management systems involved. It mandates rigorous hazard assessments, detailed operating procedures, robust mechanical integrity programs for equipment like valves and tanks, and comprehensive employee training. Bhopal underscored that safety is not just about individual components, but the entire complex interplay of a system. Bhopal fundamentally transformed the approach to industrial risk management. Companies were compelled to conduct more thorough risk assessments, implement inherently safer designs, and build in greater redundancy across their safety systems. The disaster demonstrated that the perceived cost savings from neglecting safety were insignificant compared to the potential financial, legal, and human costs of a major incident. It forced industries to acknowledge that robust safety is not an expenditure, but an essential investment in preventing catastrophic failure. The Bhopal catastrophe remains a chilling lesson in industrial history, a stark reminder of the devastating consequences when engineering principles are compromised and safety systems fail. The story of the faulty valve, the deactivated cooling, and the bypass scrubbers and flare tower serves as a perpetual warning. It underscores the critical importance of continuous vigilance, uncompromising maintenance, and an unwavering commitment to safety in all industrial operations. The lives lost and forever altered demand that the lessons of Bhopal are never forgotten. The Bhopal disaster is more than a historical event, it's a living legacy that continues to shape industrial practices and regulatory frameworks globally. It stands as a powerful testament to the fact that even a single mechanical oversight, compounded by systemic negligence, can unravel into an unimaginable human and environmental catastrophe. The meticulous analysis of the engineering failures, from the compromised valve to the deactivated safety systems, continues to guide engineers, policymakers, and industry leaders in their relentless pursuit of safer industrial processes. The memory of Bhopal fuels the ongoing fight for accountability and perpetual safety.